I'm Dan Ostrowski, one of the mechanical engineers.
I'm Tom Embor, another one of the mechanical engineers.
I'm Jeff Herman, I'm the last mechanical.
John Lolis, computer engineer.
Brian Stevenson, electrical engineer.
James Donahue, computer engineer.
Mohamed Arifin, electrical engineer.
Sashi Evsipiev, electrical engineer.
Alright. So the main objective of the project was to build a humanoid-style robot that was capable of standing and walking completely on its own. These are some of the objectives that we were trying to get. So, like I said, balance a walk on its own. One of the objectives was to recover itself from an upright position if it were to fall down. It's completely autonomous, like I said, completely untethered for up to 30 minutes. This should be able to support about 125% of its own weight on its back. It should be able to avoid obstacles. It can recognize voice commands. It is able to withstand a fall. And we ended up designing, building, and debugging this entire project up to its current state, which is 20 weeks. It holds a 2-quarter project that goes with our multidisciplinary senior design program at RIT. So yeah, 20 weeks in. And our budget, which we were aiming for, was $2,500, which was the same budget for each of the previous TigerBot families. We ended up spending about $3,100, which was slightly over, but not too much.
These are the previous TigerBots. You can see TigerBot 1 to 3. As we go across, you can see the first TigerBots used smaller servos and became more robust as they got to TigerBot 3 and on. The skeleton has got more robust as the winner. So for me as a Russian engineer, I was in charge of making the TigerBot as humanoid as possible. I chose Iron Man as a shell design, and I used a program called Papakura. It's an open source program, so it was free for me to use, and basically allowed me to print out templates and create the 3D modeling designs you can see on the left-hand side over there. And when I printed it out, I could cut out the templates and then scale it to the robot size. And for the material I made it out of, it was 0.016-inch aluminum. So the malleable enough for me to rivet and put together along with the rigidity of it.
Alright, so from a mechanical standpoint, there's obviously a lot to handle. It's a pretty big project. So we took benchmarking from those initial 3 projects and went from there. So we had a customer specification for a minimum of 20 rotational degrees of freedom. But we actually jumped up to 23 based on analyzing the way a person actually moves. So we ended up at 23 full degrees of freedom. And at each of those, we went with a full load-bearing design. So one of the downfalls we saw with previous teams was the servos actually took structural load through the output shafts. And that was our main design goal, was to eliminate that fact. In that way, we also allowed the servos to be fully floating, so we can take them out and replace them when they blow, or if something goes wrong. It's much more accessible. And the fact that they take no structural loads allowed them to be fully utilized. So we actually get a better torque output from our motors than we assumed the previous teams did. One of the other big things was keep the center of gravity low, which assists in balancing, walking, getting up, and everything that this platform is meant to do down the road. And from the servo standpoint, this is kind of the biggest part of our design. So previous teams, TigerBot 2 used a lower torque servo, about 600 ounce hitches, and TigerBot 3 actually used a higher torque servo, which was around 1,000 ounce hitches. So we actually combined the two. We ran some simulations to figure out what joints took the most torque under current situations that we wanted to do, and found peaks of around 1,000 ounce hitches in the legs. So we used the higher torque servos in the legs, and much lower numbers in the upper body, so nothing over 600. So we actually used all of the lower torque rotor servos up top. As you can see here, this is our complete Cad model. We have every component in here that we designed, did all the math to make sure we were at the right size so this thing wouldn't just crumble. We did all the design in SolidWorks. And one of the big things for us was weight. Obviously, with power limited motors, weight's huge if you want to do anything. And we actually came in at 18.5 pounds without the shell, so we're figuring roughly 19 with the shell, which is below what we were aiming for, so we're actually very happy with that. We also saw improved joint performance with a lot of freedom, made our servos work very well. And also one of the big things, we went for a modular design where, from a benchmarking standpoint, the limb choice of previous teams was different than ours. So the team that used a 4-rod design and U-channels as well. But as you can see here, we have a single rod, almost like a bone, between each joint. And that actually allows you to step up inside by simply running a saw, cutting a piece of aluminum and putting it in there. So So it's actually very expandable for future tuning. Here's just some close-up views. So on the right is a close-up of your arm, so that's actually your elbow. And here you can see a thrust-loaded joint, which is the rotation of your arm, as well as the actual elbow motion. And on the left is an exploded view of the knee, which shows every component, and it's a pretty detailed thing. So we're not going to go through all that. If you guys have more detailed questions, we'll talk about that after the presentation.
And this is the inverse kinetics walking concept. Basically, it's using half-plane inverse kinematics to show how to make a stable walking gait for a humanoid robot. And here's a video simulation done in VBox of the walking gait showing stability at different step speeds. And up there you can see the X, Y, and Z foot axes, basically showing how each leg moves over time. And it's all programmed to ensure stability with the design of the robot. And that's used basically to enable walking.
So the hardware or the computer stuff used on the internals of the robot are, we use the RoboBoard microcontroller. We chose this because it has 24 integrated PWM channels. We're using about 20, how many servos? 23 servos. So we don't want to have to worry about a controller. That's more hassle. It's all integrated on chip, so it's really easy to use, really accessible. For balancing, you always want to know where the robot position is, if it's standing, if it's fallen. So we chose a 9-axis IMU. It has the gyroscope 3 axis, 3 accelerometers, X, Y, and Z. And also the easy voice recognition, which allows us to actually give voice commands. And it comes with pre-programmed code that's machine learned, so it should work with anybody's voice here. We can also add on others by training it. The problem we ran into is that it only worked with the person who's trained its voice, which is kind of limiting since the robot should be able to use that everybody. Our software flow was this main part up here. You didn't want to move the robot if it was falling. Moving that could destroy the limb, send too much current through the servo, blowing out the servo. So you always wanted to check if it's fallen by checking the IMU, making sure it's still upright position. After that, check if there's no object in front of it. If there's an object in front, it could also cause damage to the robot or cause the robot to fall over. Or it might just be hazardous to the robot. You don't want to be walking to, say, like a dog or something, knock it off, drag it away. Then you check if there's a new voice command, because that means it'll be altering what the robot is currently doing. Once it takes the voice command, it'll process the voice command and change its current process. If not, it just keeps undergoing the current actions on. So say we have it currently for balancing. It'll continue balancing in that position without any change, and we'll keep doing that. Or if it's currently walking, it'll keep doing that until it's completed the task. And then after that, it always just makes sure it's balanced. Because if it's not balanced, the robot always has potential to fall over, and we want to keep it upright, like a human. So we always check to make sure it's balanced.
Alright, so after taking all the mechanical designs and all the specifications that the computer engineers required, such as balancing and all that stuff, we had to build the entire electrical system. So demonstrated here is the power electrical system. As James mentioned, we had the microcontroller and the Arduino and the current sense for doing the legs. Basically, my job as an EE is to power everything. So we started out with 2 batteries because one of the tasks was to make it untethered. So in order to do that, and in order to protect all the circuitry and the servos, we need 2 switches. One powers purely the logic. So for example, in the demo outside, we can do voice commands without having to worry about powering the robot's legs. The current sense board is attached to the servos, enabling it to sense how much current, or how much power each servo is drawing in the legs, which will be helpful for balancing. And as here, we have the Arduino communicating with the RoboBoard and all the sensors as well. So we have the IMU using I2C and all the IR sensors. So in order to do this, we had to make our own custom PCB boards. In order of protection, like I said, we use switches. We also have a fuse in there in order to maintain that no excess current either flows back into the batteries or into the servos damaging them. Because we're using batteries and they're kind of finicky sometimes, we had a low battery indicator to make sure we didn't overdraw the battery and cause any damage. As you can see, there's an I2C bus up there, so there's one master that's connected to the RoboBoard, and it can communicate with up to 4 devices. Current monitoring is used to determine the servo strain. So if I were to push you over, your strain, you're in your muscle, you feel that. And a robot equivalent is how much current these servos pull. So we measure each of those servos using the Hall effect on each these chips. We designed a board with 25 chips so we can do every degree of freedom if necessary for our robot. It can be used high side or low side, so either it's on the positive terminal or the negative terminal of the servo.
Alright, so the overall results in its current state, as you might have been able to see earlier, it operates completely autonomously. It's able to respond to multiple commands, especially the voice commands. And if you saw, it was able to completely stand up and balance on its own, which we're pretty proud of. We didn't get it to walk at this point, but that is definitely a future implementation that we'll have within the next week or two when this project is actually finishing up. So one of the challenges that we ran into was actually a time constraint. Like I said, this project is not completely finished as of right now. So that's definitely the biggest challenge we ran into, because if we had more time, then we could say that we could get it doing everything else that we were planning to do, like walking and everything else.
Right, and the big part of that is we have 20 weeks to make a platform for future teams. So we have set the stage for the next iteration to finish that up. From a mechanical standpoint, there's also a large manufacturing limitation to this project. As many of you might know, the way a servo motor works is it's an external spline, and in order to attach something to that, due to our load bearing design, we actually need to extend that, and we here are not capable of machining internal splines. So we get a little creative and use spring pins and some crafty drilling to make that all work, and that's kind of one of the design downfalls from a mechanical standpoint. So had we had that manufacturing capability, we were much more robust design.
So for future recommendations, if there's another iteration, I would highly recommend from an electrical point of view, as many of you have seen, there's a lot of wires in our robot. Luckily, it all works. However, debugging rat's nests and running with EE and all the electrical numbers, I'm sure now, it can be a little tricky. So ideally, from the beginning, we were going to try to go with the prescale tower layout where it's all connected, there's very little wire, very little mess. Unfortunately, we won't be able to do that in the time constraint, but that's definitely something that we should recommend looking into in the future.
So that's it. Anybody got any questions?
What can you identify because this is the 4th generation, what specific improvements have you made over 3?
It can hold itself up. So the previous TigerBot iteration, we said we were trying to make it light. So the previous TigerBot, I think 25 pounds?
Yeah.
It was a total of 25 pounds. These servos, even though they're high torque, they're still not that strong to be able to hold that up and be able to walk. So we wanted to make sure that it was able to walk and keep itself standing even with the weight it has. Because if it's too much weight, the servos will fry, or the servos will blow up, set on fire, smoke, whatever, all that fun stuff. And we didn't want that happening. Even if they're at the max torque, it would still be hard to get it to walk because we wouldn't be able to lift up the leg and get it to move. So from our perspective, we wanted to try to keep everything as light as possible while keeping the, you can talk about the load bearing also, which is another issue. The load bearing, from a computer standpoint, it would cause, even though you would set the arm to or the leg to that position, with all the load on the servo, it would actually cause it to shake a lot because it was being pulled down like this, so it's kind of rubbing against it and not actually exerting the full amount of torque that we potentially had.
Also electrically, current sensing, the previous TigerBot teams, TigerBot 2 was recently outfitted with some sort of current sensing. TigerBot 3 had limb current sensing. However, using individual servo current sensing, it's much more, the algorithm can be developed much further for balancing. It'll be much more accurate, much more reliable.
How do you correlate human movements into your algorithm inputs? How do you guys do? Is that what you use it?
Yes, kinematics. So we developed a debit hardware table for the joint structure. So when the mechanical engineers handed us the skeleton, it had set joint structures. We mapped that into the program that Sasha talked about. It's called VBots. It's simulation software. So we built up the limbs and everything. We enabled sensory feedback on those, and we tested walking out of the room. So I developed the DH table in the forward kinematics. So the foot, you can know exactly where it is. So the CEs could send a command that says, all right, 1 foot forward and then 1 foot to the side if it was falling over. So it would know what joint angles it would do to step directly to that place.
So you use that for all of your motions in limb action?
Yes.
Yeah, we're in our team. Could you describe a little bit about how you stayed organized and developed your work, track what was behind?
Very, very constant communication, definitely.
Weekly team meetings?
Yeah,
2 weeks.
2 weeks, if not more than that. We kept the constant touch, email, phone, pretty much sticking around each other's lab all the time to see what was going on every single step of the way. I mean, otherwise, it was pretty much the best way to say to get everything integrated together and get it functioning together.
We also had team members in direct correlation with each other. So, for example, the EECE correlation was quite strong, being that what sort of sensors they needed, how they needed to wire it, stuff like that. There was also a ME, make sure everything integrated smoothly. For example, if I'm routing wires to servos and the limb can't really go that way, or it's going to pinch it off, you're constantly talking and reviewing each other's ideas.
The other big thing from that standpoint is that this project is very much kind of segregated where there's that integration, but in order to get to the point where you can wire it and our computer engineers can program it, there was a huge amount of mechanical work. So the three of us that actually kind of were our own team for a long time, just doing all the design work and building things. And then unfortunately the time constraints to build something like this is probably a 20-week project. So we had to rush, build it, and give them as much time as possible and then support that. So,
You guys have input from the previous teams? Do you guys have like a kind of a grandfather and advisor?
Yeah.
Yes. A little bit.
And we were able to see their designs too. Like it was on the Cad website.
So, as I talked about in the demo, there's the Able Research Lab downstairs. That's who basically helps correlate and fund all the robotics projects within our EE department. So, all the people that have worked on TigerBot, there's been a constant stream of electrical engineers especially, and there's grad students down there. Actually, Matt up in the corner is working on TigerBot II. He was a big help in determining everything that if it's possible, if it's not possible, and the ideas. We bounced ideas off the other team, and we learned from their mistakes and took it further.
Since there's going to be a TigerBot 5, what would you tell the team, like your downfalls, what would you give them advice going forward?
I think specifically servo output coupling of servo shaft is a problem for us.
That's the only mechanical suggestion. The weight was the big issue coming into it. And I think we refined that to a point where it should be, and it actually works with the weight. But that servo coupling is the only suggestion, is to spend more design time on that. Whereas we were focused on the weight and the bearing design, which was pretty complicated in its own right. We kind of overlooked that one point because we assumed we could manufacture something that we could not, and had to adjust once we realized our capability.
Sorry, go ahead. This is the first time you had an industrial engineer on the team, so
Yes.
Yeah,
Yes.
I didn't talk about. I didn't know this major was at the school. We're not at the school, to tell you the truth. Sorry.
Did you guys integrate any other external type sensors? You mentioned detecting things in front of you.
We have IR sensors on. Right now we have it on the front. It's that optics in front. It's
right
really
under the
easy. It's actually on this one. It's right there, so it detects anything right in front of the robot. Eventually, by the end of the quarter, there'll be one in the front, one in the back, two coming up on the side, and two kind of this direction. So you kind of know what's going on all around the robot. There's also a camera mounted in the top for future object tracking. We gave the capability. We're not actually going to do that, but there is the capability to do future object tracking using that. Do we have any other? Are they putting footprints on it?
There's using the Arduino, there's many more input pins than the board can handle. So we do have the expandability to input more.
Yeah, and that was my other question. If you had a Arduino board, is that responsible for sensor handling?
Right now, only the current sensing. So we found out about 5-6 weeks into our project that full limb sensing wasn't an option, and we didn't have enough analog and digital channels on the road board. We were thinking about muxing together, but that would be too slow to get the amount of reading needed. We didn't have enough time to kind of sit down and plan out and order another board. We had an Arduino lying around, which actually had, I think the chip itself only has 8 ADCs, but it actually multiplexes on the board 16. So it's a lot quicker than us actually externally multiplexing with GPIO switching and everything. So we decided to use Arduino. It's easily able to switch out anything that can communicate over I2C. You can switch out for current sensing. We still have, I think, an opening bus or two on the I2C, so any sensor that you want to throw on has I2C communication. You just have to add any reward, the address of that, and make it communicate with the robot. So whatever net or whatever grabs gets this, whatever the design.